I
Okay.
think you can start, yeah.
Okay. Okay. Fine. So we were, see, we had essentially we were done talking about nano indentation. And I think Sushil or Prakash can let me know. Yesterday, when I logged in, you were all plotting the stress strain data and then working on doing the correction for thermal drift. So, did everybody complete that part?
Yes, ma'am.
Okay. Okay.
Apna
So,
thermal drift
so
correction we have done.
okay. So you now have data. Uh, I assume one for quads and one for a cross-linked epoxy polymer called SU8. Uh, for both these data sets, you have separated out the unloading part of the data and you have corrected that data because that is load versus displacement. So you have corrected that data for thermal drift. Okay, this part you have completed. Now, essentially what you have is a data which is free from errors, which you can now start to do analysis on. Okay, so analysis may bring on its own challenges, which is what we're going to focus on today. But at least you've sorted out other sources of error that could creep into the data. That's the part that you've completed. So I will start sharing my screen, go back to the PowerPoint. And now that you've worked with the data a little bit, if you have any questions, please do feel free to ask. So can you see my slide?
Yes, Prita, we can see.
Okay, thank you. So this, I need this slide mode. Yes. Okay, so I'm just going to repeat this a little bit. And let me just bring everything up here. So this is our goal. Our goal here is to find the essentially to find the hardness of a material. And to do this, we know that we need to figure out this thing called contact area. Okay, so this is the equation that we're trying to use. We are saying that, look, maximum load I already have from my indentation data. And I know that when the tip is indenting the sample under maximum load, the total displacement into the sample is made up of a part HC, which is depth, which is in contact with the tip, and HS, which is sink in. This is elastic and it is not in contact with the tip. So if I can figure out this HC, then as a function of contact depth and knowing the geometry of the tip, I can calculate the contact area, which is this what gray triangle is meant to show. Okay, so because I know my tip geometry, I know the angle which is made by the three faces of the tip, I can calculate the contact area as √3/4 a square. Okay, where a is one of the edges of this equilateral triangle, which you can also see here, that this is tip projected area right here. Okay, now, but to do that, I need to know what this HC is. And we said this, we are going to take it as a given because people have worked through it, they've solved it, they have said, they've shown that if I take the maximum depth and I subtract this quantity, 0.75 into Pmax divided by S, where S is slope of the unloading curve, then this quantity is equivalent to this elastic sink-in and I'll get my contact depth. Now, once I know my contact depth, if I had an ideal tip, if I had a perfect tip, then the first part of this equation, right, 3 square root 3 tan square of this should have been sufficient. It's not letting me write there. Okay, this part. And then you see there's this whole long polynomial in the box. And I need to bring this in. I need to use these terms because these are correction terms. Because my tip doesn't end in a point, my tip is blunt to start with. And as I use the tip, it keeps getting more and more blunted. So I have to periodically calibrate the tip to account for that tip blunting. And Again, for our purposes today, this calculation has already been done. And I think you would have been given these constants, or you will be given constants today. You've already corrected your data for drift. Now, the only thing that is left for us to calculate is the slope of the unloading curve. And then we are set. We can move on with our hardness calculation. Okay. Now, this is the slope of the unloading curve. If you can see here, this is now your corrected data, we assume. You conventionally, you fit or we fit to this unloading data what you see as the red curve. Okay, we fit a quadratic equation to this unloading data. So we get P load as a function of H. And once we have that equation, we know all terms in that equation from fitting to the data. This quantity S that we are looking for is nothing but dP over dH. Okay, it's the slope of this unloading curve evaluated at the point when maximum load is applied, when P is equal to P max. Okay, so this part you've already done, so we can skip all this. This is what you would conventionally fit. Okay, you would fit P is equal to, sorry, it's not quadratic, it's a power of it. So you would fit P is equal to A into H minus HF into M. What is HF? HF is where we finally land up, the final depth. Okay, and we do this H minus HF because we are assuming that from any depth H here, H minus HF is what is being recovered during unloading. So that is elastic. Okay, and load is a function of this elastic part of the displacement. So that's what we are after. So we fit this and we've obtained A and M as fitting parameters. And I think as the first exercise, we are just going to fit this. And here is shown to you an example fit that we fit this to the unloading data. We fit this polynomial. We obtained A and M. And then we calculate what is called the residual, right? That now I have an equation of P as a function of H. For every H, I can calculate a P from the fitted equation, right? And now if I look at the difference between the P fitted and P experimental, if it is a good fit, then those residuals should be randomly distributed about 0, right? Some points are fit perfectly. They can be perfectly calculated from my equation. So the difference between the fitted data and the experimental data is 0. Some points will be to one side of your fitted equation and some points will be to the other side of the fitted equation, right? That is what you do when you do fitting in a least square distance minimization kind of a sense. So this is what the residuals should look like, randomly distributed about 0. And I think Professor Gururajan has spoken to you about fitting in other context. So we are just evaluating how good a fit we have been able to do. And what you will see is that you please do this fit to your quads data first. Evaluate these residuals, plot the residuals, and if they look like what you're seeing on your screen right now, then we are good. You know, we can then go ahead. You take the first derivative of this, right? It becomes AM into H minus HF to the power M minus 1 and evaluate it. And there you have your S. Put S in the equation that we had earlier. You have your contact depth. Take contact depth, put it into the area of contact equation. You have your area of contact. And finally, you have the hardness. We are done. Now, in our case, when we were doing experiments on this cross-linked epoxy, what we found was that, good afternoon, Mr. Badrinarayan. I'm sorry, I've gone ahead with teaching a little bit. I'm sure Sushil and Prakash will be able to get you all caught up. Otherwise, I guess you can ask questions a little later. So I'm trying to finish the part that I have to teach so you can all get along with the exercises. So for SU8, what happened was that we did the same fit, okay? And if I just look at this visually, the red curve and the black curve here that you see, looks like a good fit to me visually, right? But then we again calculated the residuals, P fitted minus P experimental, and you see there's a pattern here. And that's not good. A systematic pattern in your residuals tells you that you are not doing a good job of, minimizing distances from fitting points when you're doing your fitting. So what I decided was to try something which is called LOS. And I think R Studio has this as a built-in smoothing function. Now, what this does is it's still regression. But what you do is you don't fit the entire range of data. You don't even fit, say 90% of your data. You fit it piece by piece. And what that does is that it removes these systematic errors that would arise from fitting to the entire data. Okay, so it's like a piecewise smoothing of your data. And we can show you the results of our lowest fitting. Here they are. You still see that the residuals go up as we go deeper and deeper. But remember that unlike quads, SU8 is a material where the properties are also depth dependent. Okay, it's a viscoelastic, viscoplastic material where deformation is time dependent, and we also expect that the properties are probably changing as a function of going deeper into the sample. So we're not worrying too much right now about the fact that the residuals increase a little bit as we go to higher depths, but at any depth, they are randomly distributed about zero, higher as, positive values as well as negative values. So we are happy with that. Now, I understand that you come from very varied backgrounds, and the examples that we've taken come largely from material science because that's what our background is. So I was just looking around on the internet for information on LOS, and I just took this data from some source. Okay, sorry, let me just finish this. That we can also calculate the reduced elastic modulus. So once you have S and you have area of contact, besides the hardness, you can also calculate the modulus, but that's just for information. One more quantity that we can get. Okay, so I was looking around for data for more information, and I found this PDF document. It's some statistics site where they're talking of skin cancer, incidence of skin cancer, melanoma. Okay, and this is the data. Here is year, here is incidences of skin cancer. And if you again take the whole data and you just fit to it, the fit would look something like this, right? And this fit captures the general trend of data. It says that, okay, over what is this, from I think 1950 to about 1970 or so, or yeah. So we have rather, 1931, 32 to about 1970, the incidences of skin cancer are increasing. On an average, there is an increase, right? But you can very well see from the data that this is not a smooth increase, right? There are these excursions. There are these peaks that occur, which are not captured by this generic fit, which does capture the overall trend of the data, but it's making us miss certain details, right? So now this is a comparison of using LOS to fit. And you see here, they have something called a smoothing parameter. And smoothing parameter is essentially what fraction of your data are you using to fit. Okay. So it's how many data points are you fitting at one point in time multiplied by some constant gives you the smoothing parameter. Okay. So this increases. Point one is essentially you're fitting to every data point. So you have a great fit, but this is an overkill. You don't need to fit to every single data point. As you start using greater and greater pieces to fit, at one point in time. So I'm going to fit the first 10 data points, then the next 10 data points. Now I'm going to fit in smoothing parameter 0.3. Let's say I'm going to fit first 20 data points and the next 20 data points. What you see here is that now this fit does start to capture these variations in data, right? So this is 0.2, this is 0.3, and again 0.4 is getting fairly close to what we had earlier, which was, let me fit the entire data, which shows the trend. Now, what these excursions were related to, as people later found out, was that it was I think a 10-year, that every 10 years there is an increase in solar activity. And that increase in solar activity corresponds to an increase in instances of skin cancer. Okay, so these small peaks corresponded to those flares in solar activity, which would be completely missed by this over smoothing that you see on the bottom right panel. Okay, so this is just to show you the merits of using lowest fitting as opposed to using a general, say, second order polynomial or a third order polynomial. These again are the residuals. Like I said, the first fit is that I'm fitting to every single data point, so the residuals are 0. But then why am I fitting? If I have to consider every single data point, I'm not really looking for trends, right? In this second, the top right panel, you see that some of those trends do start to get captured in the residuals as well. They're stronger in this, the bottom left panel where the smoothing parameter is 0.3. And then, of course, by 0.4, the residuals are larger. But you also, again, missed the trend. So somewhere here, one has to use one's judgment as to which is the smoothing parameter to fit. And you will see that when you work with our SU8 data as well, you could fit to 10 points, you could fit to 20 points, 30 points. What makes sense? What's the, and there isn't necessarily one recipe for that. You try it out and then you see what you get.